This section is about Newton's second law and about how we make simple models out of a complex reality. This time, imagine that you're in your spacecraft and your orbital velocity is not big enough to stay in orbit. This time, you will indeed accelerate to Earth under gravity. However, apart from gravity, there is another force acting now, and it's called drag or air resistance. In space, this force doesn't exist because space is a vacuum, there is no air. By contrast, the Earth's gravitational pull is big enough to hold an atmosphere of gases around it. This is lucky because these gases are essential for life on Earth. They are nitrogen, oxygen and argon, with some water vapour and tiny amounts of other stuff like carbon dioxide, neon and helium and methane. A spaceship falling at great speed through the atmosphere will induce a resistive force because it has to push these gas particles out of the way. We know the forces acting on the spacecraft. They are gravity and drag. If we know the total force, then we can calculate the acceleration. The acceleration is how fast the velocity changes. The relationship between force and acceleration is given by Newton's second law and is force equals mass times acceleration. If there were just gravity acting, this would mean that the spacecraft was continually accelerating. It would get faster and faster and faster until something slowed it down, like hitting the Earth's surface. However, since there is air resistance, the total force and therefore the acceleration changes. Experiments have shown that air resistance is proportional to the velocity squared. This means that the bigger the velocity is, the bigger the air resistance force is. Eventually, this resistive force gets to be equal to the gravitational force, and the total force becomes zero. Once the total force is zero, the acceleration is therefore zero, and therefore the velocity doesn't increase anymore, and this is known as terminal velocity. In fact, this is a very simple model, and air resistance depends on much more than just velocity. Aerodynamic shapes that cut through air have low air resistance and therefore reach high terminal velocities. In contrast, bluff shapes, like parachutes, have high drag and therefore they reach low terminal velocities. Newton's second law is important to us because it gives us the acceleration, which means we can then work out where the spacecraft is at any time, how fast it's going. This means that we can tell when it will hit the Earth and where. The terminal velocity is useful because we can tell how fast the spacecraft will be going when it hits the Earth, and therefore what momentum-reducing force it will be exposed to on impact. We said that our model of air resistance was simplified. It depends on the shape of the object as well as the velocity in reality. There are other things missing from our simple model too. For example, the strength of the gravitational force changes with height away from the Earth. Gravity follows an inverse square law. This affects both the acceleration due to gravity and the density or thickness of the atmosphere, and therefore the drag. In mechanics, we can often ignore complicating factors like these to make simple mathematical equations that we can solve. The important thing here is not to get rid of anything too important so that your simplified model doesn't actually predict what happens in reality. An object reaches terminal velocity when its weight balances the drag because the total force and therefore acceleration are zero.